Good morning. I'd like to thank you all for being here today. I'm John Hellman. I'm the Senior Associate Dean and Professor of Material Science and Engineering in the College of Earth and Mineral Sciences at Penn State. And I'm honored to be here today as the tutorial and memorial lecturer for the Arthur L. Friedberg Ceramic Engineering tutorial. Before I get on with the presentation, I'd like to acknowledge our colleague and friend, Art Friedberg. Art received his bachelor and PhD degrees in ceramic engineering at the University of Illinois, with shorter stays at the University of Chicago and Scripps. He served as a ceramic engineer at Stone & Webster Engineering Company and subsequently the Elwood Ordnance Plant before leaving for service in World War II as an aerologist and officer in the U.S. Navy, where he served in Pearl Harbor and on Guam. He returned from the war to become a professor of ceramic science and engineering at the University of Illinois, where he spent a long career of 33 years, serving as department head and an advocate for modernization of ceramic education at the University of Illinois. Art was a longtime ACerS member. He's a fellow of the American Ceramic Society, a leader in our National Institute of Ceramic Engineers, and also in the Ceramic Educational Council. And he served a 5-year stint as our executive director from 1979 to 1964. He's been a mentor to hundreds of students and professionals. He's a very warm, compassionate, thoughtful, conscientious man, accomplished musician, outstanding father, and dependable friend. Unfortunately, Art passed away in 1984, but his memory lives on. In reading through his biographical information and so on, I came across numerous quotes and accolades regarding just how wonderful a man Art was. One really stood out, one by one of our icons of ceramic engineering, Mal McLaren. He said, Art was an outstanding educator, administrator, and a scientist whose skills were so well balanced that his enormous productivity appeared easy. That's a wonderful accolade, and it's in that spirit that I am humbled and honored to be able to give this year's memorial lecture. I'd also like to acknowledge my collaborators in this work. This work started while I was at Sandia National Labs back in the early 1980s, where I worked with Paul Lava, Mike Etaw, Rod Mahoney, Vicki McConnell, Bill Smith on some of these materials I'll discuss today. At Penn State, I collaborated with Barry Sheets, Bruce Miller, Paul Painter, and Terry Engelder, and my students Walter Lucier, Ryan Koseski, David Hartwich, Peter McClure, and Al Siegel in the development of these materials, the characterization of the processes and the like. We had numerous industrial interactions, most notably with MoSci, where we worked with Ted Day, Joe Szabo, and Stephen Jung, and at A&H Refractories, now Harbison Walker, Mark Palmiciano, and David Hartwich. The support for this work came from a variety of industrial sources like Halliburton and Carbo Ceramics and Nittany Extractions Technology, LLC, Harbison Walker, or A&H, and then from federal and state government like Department of Energy and the Ben Franklin Partnership of Central and Northern Pennsylvania. And it's with special thanks to the American Ceramic Society's Education and Professional Development Council that I'm here today to tell you about this work. Thank you very much. How did this work start? Early in the 1980s, while I was at Sandia, our group was tasked with finding a ceramic solid thermal transfer media for a solar central receiver concept. In this concept, ceramic particles were to be dribbled through a insulating or a solar beam, a concentrated solar beam that was derived from acres and acres and acres of heliostats or mirrors. This roughly 10-meter tall aperture through which the particles were irradiated yielded a residence time sufficiently long such that the particles would increase in temperature from about room temperature to on the order of 1500 degrees C, a very, very high intensity solar beam. These hot particles then would subsequently be stored and energy extracted from them to do industrial processing, such as cracking ethylenes, and then recycled through the system repeatedly over the lifetime of the system to capture the solar radiation, transform it into thermal radiation for industrial processing. The charge, the batch of ceramic particles that would go into the system was on the order of 12 million pounds. That's a large volume of materials, so it needed to be relatively inexpensive, obviously very refractory, and mechanically and thermochemically robust to withstand repeated cycles over a lifetime of several years. So we examined particles that would be available from the abrasives industry, and there was no shortage of materials that we could use there that had the requisite properties of refractoriness and high strength and even solar absorptivity. However, due to the nature of abrasive particles, they were angular. And the angular particles, when they fell the 100 meters through the solar central receiver during application and so on, would indent one another, causing cracking, which would contribute to failure and subsequently the generation of fines, which would increase the susceptibility of the materials, the particle bed, to sintering, something you didn't want. This bed needed to remain freely flowing for multiple recycling through the process. Therefore, we felt the need for using, or we determined the need to use spherical ceramic particles. Spherical ceramic particles on the sizes necessary here, something on the order of 1 millimeter in diameter, were not readily available in the ceramic industry at the time, with one potential exception. And that exception was a new family of materials that were being developed for the stimulation of gas and oil wells. These materials were known as proppants. They were manufactured from ceramic materials in a spherical form and were becoming available on the market in the quantities necessary for use in the solar central receiver. So we were able to demonstrate that technology, and it worked out well. About that time, I moved back to Penn State, started my work there on the faculty, and decided that I would like to continue work on the proppant materials for the oil and natural gas industry. And here's why. Evolving at that period of time was new technology such as directional drilling and hydrofracturing, which was going to enable production of gas in a more economical fashion from gas fields that were not traditionally tapped in the past because the vertical drilling technologies was just not appropriate for economic recovery of the gas. The horizontal drilling technology and hydrofracturing opened up these gas fields, some of which are shown here on this map of the United States. Now, some of these you've clearly heard about over the last 10 to 15 years. For example, the Marcellus Shale and the Utica Shales up in the northeast of the United States. These gas fields contain sufficient gas to enable all of our energy requirements, to satisfy all of our energy requirements for something on the order of 150 years. But were only retrievable through the use and combination of several new technologies. Similar gas fields exist throughout the rest of the United States and indeed around the world. What this means is that the technologies need to evolve to be able to extract the gas from the porosity in these shales. This is a picture of a Marcellus shale showing the pores in which gas is trapped and which you need to access during the drilling process via creation of new surface area, the whole purpose behind hydrofracturing. This shows a Marcellus shale outcropping in New York State, which you can see clearly the sedimentary nature of the rock or of the shale, as well as vertical fracture traces which are common in the Marcellus Shale. These fracture traces are oriented roughly northeast and northwest. Those outcroppings that exist are essentially degassed due to these vertical outcroppings and the like. And it's the deeply embedded shale deposits that we're after for production of natural gas. But the way you get to it is to create cracks in that shale so that you can retrieve the natural gas using processes combining directional drilling and hydrofracturing. Directional drilling is shown in this cartoon here, in which a gas well is sunk vertically and then turned to follow the moderately undulating, nearly horizontal deposits of shale in which the natural gas is entrapped. These deposits are on the order of 6,000 to 8,000 feet deep. And so this is a very long drill string that once turned can extend on the order of a couple miles. Those drill strings or those drill bores are then cased with steel, cemented with grout to the surrounding rock so that you have a relatively impermeable barrier and hermeticity to the surface so that you can avoid contaminating groundwater. You then subsequently introduce shaped charges into the wellbore, and these shaped charges are used to blast holes through the wellbore, creating fractures in the surrounding shale. Those fractures in the surrounding shale are what release the natural gas from the shale to the wellbore. But the intent is to increase the size and length of those fractures in the rock to be able to achieve more surface area and retrieve more gas. Hence, hydrofracturing is employed, where millions of gallons of water laced with ceramic particles known as proppants are injected into the wellbore. The wellbore is then pressurized, and these cracks that were created by the shaped charges expand, grow, and are held open by the ceramic particles in the hydrofracturing mix, the proppants. So the intent is that for a proppant to perform well, they need to be sized in the range of about 0.5 millimeter to 2 millimeters in diameter. They need to be strong, easily transportable, robust in downbore chemical environments, and available relatively inexpensively. That's an important characteristic because something on the order of 1,500 to 3,000 tons of material are used to develop a single gas well, depending on the number of stages of fractures that were done during the shaped charge blasting process. This is a large amount of material, so manufacturing capacity needs to be available and the costs need to be moderately low. But back about the time that these unconventional natural gas and oil fields were starting to be developed, the proppant demand worldwide was on the order of about 10 billion pounds per year. As these emerging plays developed, that increased tenfold. There was a rush on for materials that could be used to prop hydrofractured gas wells. And the conventional raw materials that were used as proppants, like the Brady and Ottawa white sands, kaolin and bauxite sintered engineered proppants and the like, were experiencing very rapid price increases because of their limited availability and new demand. So alternative raw materials, which are closer to the site of application, indigenous perhaps to the area where natural gas development is occurring, were needed to permit development of these new energy resources. So the research activities we embarked upon were severalfold. The first was to take a look at the conventional commercial proppant materials and manufacturing processes for those. We were interested in understanding more about the compositional and microstructural modifications that would enable higher strength, lower cost of production, and greater performance. We concentrated that work on the sintered bauxite and kaolin-based proppants that were commercially available state-of-the-art materials, vintage 2002. We also looked at non-traditional raw materials that are actually waste streams, byproducts of other industrial processes. For example, mine tailings, drill cuttings from drilling wells, domestic recycled glass, fly ash from coal combustion, slags from metallurgical processes. These are typically materials that are put to landfill at significant cost and significant environmental impact. And we thought if we could transform those into useful value-added materials via good, well-informed ceramic processing technology, that we would have new value-added products that basically are removed from the waste stream, giving significant economic and environmental benefits. The whole thrust in this work was to tailor the mechanical and physical properties of the materials through compositional and microstructural control. And we practiced this work in several different families of materials: ion exchange glasses, glass ceramics, and sintered ceramics. And I'll tell you a bit about all of these. In the first case, where we wanted to examine what processing modifications could be done to enable us to manufacture proppants cheaper and with a lower environmental impact, we practiced this on bauxite and kaolin-based proppants. These were commercial materials where we expanded the range of sintering temperatures, sintering times, and interestingly, the heating rate to get to the sintering temperatures. The heating rate is an important characteristic because these materials are sintered in large rotary kilns, much like a cement clinker manufacturing process. And therefore, not only the temperature that you go to, but the residence time of the material during the sintering process has an impact on the amount of hydrocarbons that you use as the fuel to heat the process, as well as the CO2 that's generated during the process. So lower sintering temperatures and shorter sintering times, which could be achievable by higher heating rates, are good things to consider, provided the mechanical, thermal, and physical properties of the resulting proppant is not modified. So we were able to demonstrate in the case of bauxite and kaolin ores that we could sinter the materials at substantially lower temperatures by manipulating heating rates, going to higher heating rates, and achieving fine microstructures, fine grain size microstructures, appropriate crystalline phase assemblages, and specific gravities to yield high compressive strengths. This was good news at the time. Industrial processes were able to be modified, economic benefits and environmental benefits were achieved. Well, in the course of doing this work, we thought, what could we do to improve the sintering process even further, to permit even lower sintering temperatures and perhaps even finer microstructural evolution? And so we embarked upon processes whereby we, recognizing that the materials sinter via a liquid phase sintering mechanism, we could decrease the viscosity of the liquid phase during the sintering process, increase ionic transport, and indeed also take advantage of transient liquid phase sintering mechanisms to yield high degrees of densification, appropriate phase evolution, and high strength proppants. We looked at systems in which potassium oxide and iron oxide were deliberately doped into bauxites and kaolins at levels higher than what were considered to be excessively high impurity levels by the proppant industry at the time. This was a hard sell in the beginning. Why use more impure ores to make these materials than what was typically used in the past? Well, the driver on that was also economic, because the ores that were available outside of our domestic confines of the continental United States had higher levels of potassium and higher levels of iron oxide, and in the past did not result in or allow production of proppant particles of sufficient mechanical properties for use in the oil and gas industry. So we embarked upon a series of experiments in which we dramatically expanded the level of dopant concentrations outside of the common impurity levels. We exploited transient liquid phase sintering to achieve high levels and rapid densification, at the same time achieving requisite crystalline phase assemblages to achieve high strength. And some interesting things cropped up. We were able to densify the materials at a couple hundred degrees lower than what was traditionally being used in the proppant industry to get full density and high strength, strengths commensurate with the very best commercial state-of-the-art materials. The interesting thing that we also saw is that in these dense particles, at the conclusion of the sintering, they were oftentimes decorated with metallic iron, which was a bit surprising to us because the sintering processes are done in a combustion environment, where the combustion environment is relatively oxidizing. We didn't expect to see metallic iron. We redid the experiment several times because we didn't believe the results. And indeed, every time the same result cropped up. So we dug further into the literature going back to the 50s from the refractories industry, in understanding the interactions between fire clay refractories and bauxite-based refractories with molten iron, steel, and slags. And what we found is that the occurrence of these metallic iron decorations on the surfaces of our particles was entirely expected if we understood more about the oxygen partial pressures through the course of the processing cycle in which these proppants were manufactured. And so we thought this would be an opportunity. Could we exploit those iron decorations to re-react with the material in subsequent phases of the sintering cycle to form a dense outer core and potentially a porous or a dense outer layer shell and a potentially porous inner core? And indeed, we were able to do that. And here's what we saw. If we started with a fully densified proppant particle achieved by our sintering process I just showed you, and then subsequently reheated it in a controlled oxygen partial pressure, we could evolve porosity in the interior of the particle while maintaining a dense outer shell. We studied the kinetics of that process and found that the activation energy of the pore evolution was on the order of 500 kilojoules per mole, which is comparable to the creep activation energy of aluminosilicates of this composition. This is an interesting result because it supported our hypothesis that the evolution of this porosity in an already dense ceramic was the result of evolution of oxygen, blowing bubbles, if you will, in the interior of the ceramic particle when you process the material in a controlled oxygen partial pressure. This was borne out in subsequent studies, and it allowed us to manufacture proppants with what we term the core shell microstructure, where we take a ceramic particle or proppant, sinter it to full density, and then de-densify it while maintaining a dense outer shell. This yields a hermetic particle with controlled specific gravity to the point where you can make a neutrally buoyant ceramic proppant, a proppant that floats in water, which has significant environmental benefits as well as economic benefits, because most hydrofracturing liquids are laced with different chemical species to promote the suspension of the proppant particles in the hydrofracturing fluid during the injection process. A neutrally buoyant particle will require fewer of those chemicals, a significant environmental impact improvement. Similar results were achieved in the doped kaolinites. We were able to sinter these at substantially lower temperatures, and we were also able to achieve the malted milk ball or core shell microstructures in these materials by exploiting the use of the iron oxide dopant. Well, we patented that work. That work was subsequently licensed. It's being exploited in the manufacturing of controlled specific gravity high strength proppants right now, which are being used around the world. We shifted our attention or continued our attention into other materials. I'm going to tell you a bit about each of these: ion exchange glass for use as proppants, glass ceramics derived from mine tailings, and glass ceramics derived from drill cuttings from wells. Let me start with the ion exchange glasses. Glasses have been considered for use as proppants for decades. Glass particles that are highly spherical can be manufactured in very high strength form using flame spheritization processing. They're readily available and available in the kinds of quantities that would be commensurate with use as hydrofracturing additions. However, they don't work. And they don't work because they're such high strength. What happens to a glass particle when used as a proppant is that when the pressure of the overburden, the closure stresses in the well, is significantly high, on the order of 6,000 psi or so, these beads fail. And when they fail into very, very small particulates. These small particulates are the result of the high stored elastic strain energy at failure. Those small particulates in turn blind the interstices in the remainder of the prop particle bed, and as a result, the permeability of the bed is decreased, thereby decreasing the production rate of the well. So glass is not used as proppants. That's unfortunate because domestic glass recycling streams are enormous in the United States, and they're ubiquitous. They're all over the place. They're indigenous to areas where natural gas exploration and development is occurring and could be readily exploited if they could be made to work properly. So we hypothesized that we could modify the behavior of glass particles by engineering stress profiles in the proppant particles in such a way to make them fail into large chunks instead of fine particulates, and those large chunks would continue to prop. This work was inspired by things that were being done by my colleagues, Dave Green and Jun-Woo Shen at Penn State at the time, on engineered stress profiles in reverse ion exchange glasses. We thought that we could apply the knowledge that they were generating there to the development of a new class of proppants based on glasses, which would perform in an admirable way. And this would be done by modifying the fracture morphology and hence prolonging the permeability of prop formations. This cartoon here shows you what the concept would be. That is, we would start with a proppant particle manufactured from glass in which we remove some sodium, replace it with potassium using a molten salt ion exchange process, and then using a reverse ion exchange process, put some of the sodium back. What this would result in is a tensile region at the surface and an embedded compressive stress field in the proppant particle, which would have a couple of benefits. The first is the inherent flaws at the surfaces of the glass particles would all grow to a finite uniform length. They would arrest at the boundary between the tensile and the compressive stress field, yielding a very highly reliable particle, high uniformity of strength, and potentially stronger as well. Right? Secondly, the compressive stress profile and transition to the tensile stress field might contribute to an onion skin failure type morphology, in which the outer layers of the particle would flake off during compressive loading, leaving behind a large inner core, which could still prop. And that was verified using finite element analysis on ion exchange glasses, that this failure process could indeed be stimulated. These are from finite element modeling of compressive failure of beads of glass particles using an API 60 test methodology. And we thought that we'd be able to accentuate that through the use of a reverse ion exchange process. So we procured glass cullet from the domestic recycling glass industry. This is glasses of a variety of colors, all from your beverage containers and the like. So you'll see green, you'll see brown, you'll see clear, occasionally even blue. We worked with MoSci then to sphericize these using their flame spheritization processes. We characterized their chemistries, which was an important thing because we needed to know how to ion exchange the materials to different levels of starting flaw depths. So we used this information to calculate things like strain temperatures and temperature time behavior necessary to embed a compressive stress field at a depth of 1, 3, 4, and 5 times the initial starting flaw depths. We used Weibull analysis to characterize the strength distributions. These are Weibull distributions based on hundreds of individual fractures in diametral compression of a variety of different glass bead materials. We use this methodology throughout because it enabled us, number one, to understand the characteristic strength, number two, understand strength uniformity, and number three, we could then use that data to calculate the onset of failure and strength of any bead of comparable composition and treatment, but of a different size or under a different loading characteristic. We found that colors behave similarly. There was no difference. We don't need to separate the different colored glasses for this application. And that single ion exchange yielded strengthening as was expected. And reverse ion exchange enhanced the reliability, also as we originally hypothesized and has been seen on other types of glass articles. Furthermore, longer reverse ion exchange processes yielded increased occurrence of type 1 failure. Type 1 failure is the failure of the proppant particle into large chunks, not fine particulates. Type 1 failure is desirable for their application as proppants. We verified that this failure process was indeed occurring using interrupted load tests. This particular bead was stressed to on the order of about half of its characteristic strength, and then fractography was performed. We also employed American Petroleum Institute standard test methodologies to understand how these proppant particles before and after ion exchange performed in crush tests. Now, a crush test from the American Petroleum Institute entails taking an assemblage of beads in a die, applying a uniaxial load to different levels, sieving the materials in between loads, and when 10% of the materials is produced as fines, that's considered the crush strength. Pretty empirical, but it's used widely by the industry. And what we were able to demonstrate was that our ion exchange glasses outperformed things like sand and a few other materials that were available for use as proppants in large tonnage quantities. These materials perform well to circa 8,000 psi, which is good news. Those are pressures that are consistent with their use in both the Utica and Marcellus shales and perhaps even out in the Bakken. We then moved on to understanding how these materials behave with respect to permeability. Liquid and gas permeability is measured using an American Petroleum Institute 61 standard test that's now known as the ISO 13503-2 test, in which an assemblage of particles is constrained in a steel die and a uniaxial load is applied via platens. A liquid solution of KCl in water, potassium chloride in water, is passed through the particle bed, and pressure drops are measured using pressure transducers. Using this, we can calculate, and using Darcy's law, the permeability of that packed particle bed as a function of the uniaxial load. And that will tell us how useful that particular proppant particle type is for use in stimulating oil and gas wells. These are some of the results that we achieved, and basically what we found is that the ion exchange glasses perform admirably well. So do some of our other materials relative to high strength ceramic proppants manufactured in industry, and that they're performing this way without the application of coatings, which is a common practice for high performance proppants in the industry. Coatings are typically phenolic resins, and they're expensive to apply. If you don't need them, don't use them. These materials outperform sands, which is good news. We can use these to prop to deeper depths for longer periods of time. So these were all great results. The ion exchange processing looked very promising. The strength testing confirmed the failure mechanisms we proposed, and we had acceptable strength retention. We verified using the engineered stress state, finite element analyses and the like, that we can promote type 1 failure and prolong conductivity in packed beds. Excuse me. However, these are ion exchange glasses. They need to be manufactured in 1,000 tonnage quantities. That's a large amount of material. And it's an engineering challenge to ion exchange and reverse ion exchange that quantity of materials, and that might impact the economics of the process. At the same time, we were working on other materials, so we segued into those that paid more attention. Glass ceramics derived from aluminosilicate byproducts of mining operations is where we directed our attention next. These are materials that are derived from what are essentially basalt compositions. These basalt compositions started as volcanic glasses, which subsequently then crystallized over the eons to form the basalts we're all aware of. So things like andesite, rhyolite, and basalt are the areas that we worked with. Why? Because these materials are available in massive quantities as an industrial byproduct of the roofing granule industry. Materials like basalt, andesite, and rhyolite are routinely mined, crushed, sized to a particular size fraction, and then used as granules on asphalt shingles used in the building industry. The issue is that during that crushing and grinding process, we generate something on the order of 40 to 50 weight percent fines that are too small for use in the roofing product. Therefore, these are put back to landfill at very substantial cost, something on the order of $9 per ton transportation costs back to landfill. So these materials should be available relatively inexpensively and in massive quantities, millions of tons per year. So we procured some of those materials. We transformed them back to the obsidian-like glass that they started as, using a flame spheritization approach in the laboratory, resulting in beautiful ceramic or glass spheres, very, very high strength on the order of 600 megapascal compressive strength, uniformly sized, and in massive quantities of 3 to 4 teaspoonfuls per day. But that was enough to do PhD theses. And what we hypothesized was that if we could take that vitreous material and subsequently devitrify it to the crystalline phases that it wishes to be in, that we could alter the fracture mechanisms in such a way to achieve a higher toughness while retaining some strength, and that these beads would fail in that type 1 failure mode that's desirable for propping. So we did that. We examined the time temperature transformation behavior of, in this case, an andesite-based material, found out where the different crystalline phase fields were accentuated in time temperature behavior, manufactured materials in those regions, and examined their characteristic strength using the Weibull approach I mentioned previously. Characteristic strengths were quite impressive, on the order of intermediate strength proppants, commercially available in the industry, state-of-the-art stuff, and that the fracture was substantially modified after devitrification, going from, in an untreated glass particle shown in the upper right, fine particulate failure that's undesirable, type 2, to the type 1 failure, large ceramic particles which still prop. This was then reflected in the enhanced permeability of these materials, which compared very, very well with industrial materials that were being supplied as proppants to the oil and gas industry. We extended this work to metabasalts because that particular mining operation was closer to us and closer to the Utica and the Marcellus shales. We did the same result, or found the same result on time temperature transformation. And we were able then to map out regions of time and temperature, which would yield high strength and at the same time, high type 1 failure. So we patented this technology and we spun it out for commercialization in a startup company because we felt the material properties would be sufficient for widespread application in the propping industry. We compared these materials using the ISO 13503-2 or API 61 permeability test. We found that these materials, which we're now calling pen prop, which was a trademark name developed by the Nittany Extraction Technology Company, performed very, very admirably well compared to state-of-the-art proppants that were readily available at low cost in the industry, and that these materials were performing this way without coatings. The pen prop materials did not need coatings to perform as well as the industrial materials that were available. So this devitrification processing allowed us to form a glass ceramic process or glass ceramic material that failed in type 1 mode, possessed high enough strength and great permeability relative to commercially available materials. So we scaled up. To go from the teaspoonfuls per day or week to tonnage quantities per hour required industrial manufacturing capacity, which we were able to access through a collaboration with ANH Refractories, now Hargis and Walker again. This is a flame spheritization tower that was developed back in the 60s by ANH for manufacturing expanded kaolin-based products for insulating refractory manufacturing. Well, we used it to go ahead and do a flame spheritization drop tower approach, much like you would make lead shot for shotguns, in which we granulated the metabasalt powders using pan mixing processes to form large granules on the order of 1 millimeter or so in size, and then dropping them through the hopper at the top of the tower. The tower then consisted of 32 radially oriented gas burners, natural gas fired burners, firing at roughly 1 million BTU per hour firing rate. Those particles would melt, fuse, spheritize due to surface tension, solidify on falling down the tower, and be collected at the bottom on a vibratory bed and transported out of the furnace in such a way that we could retrieve the materials for characterization. If you look closely at this particular photograph, you'll see lots and lots of vertical striation. That is actually the falling particle rain, the incandescent particles, essentially obsidian-based glass particles falling at the base of the drop tower. So it was a pretty impressive process, and we were able to demonstrate the capability to manufacture tonnage quantities per hour in this fashion. This is a picture of the granules before they were spheritized and after spheritized. Very, very uniform particle size, excellent vitreous particles that subsequently we would heat treat for subsequent testing and use. So our latest efforts have focused on using that technology on transforming another raw material, drill cuttings from Marcellus wells, into proppants. When you drill a well, you basically bore out sandstones and shales from the bore, what becomes the bore, transport them to the surface with your drilling muds, and then dispose of them. All right. These drill cuttings are produced in pretty massive quantities, well over 1,000 tons per well. And they contain naturally occurring radioactive materials and residual mineral oils. So when they're transported to the surface, they have to be shipped to engineered waste landfills and sequestered as a residual waste. This is a material that costs money to dispose of, on the order of $50 to $80 per ton, and is readily available in areas where you're drilling the wells. Therefore, if we could find a way to convert those drill cuttings into proppants and put those proppants back into the formations from whence they came, we would experience significant economic and environmental benefits. We felt that we were able to do this by marrying a couple of technologies that were evolving at Penn State at the time. The first being the flame spheritization approach I've already shown you, and the second being ionic liquid separation of oils from particulates. This was technology that was being developed to beneficiate tar sands from Canada, to remove the bitumen-based materials from sand and clay particulates that were mined in the tar sand region. The approach that we used was necessary because this is what a drill cutting looks like. When it comes to the surface, it's a black paste of shale particles suspended in mineral oil and containing other things like sandstone. We need to transform that into a dry powder particle for processing using conventional ceramic processing methodologies. We did it using an ionic liquid separation process that was being developed at Penn State for the tar sands programs. And this test tube on the right shows the result that you get when you use ionic liquid separation of bitumens from ceramic particulates like clay and sand. The bitumen and some solvents are shown in the upper layer. The ionic liquids are in the middle. And then the sediment at the bottom are the sands and clays. Now, in the case of tar sand separation, this is desirable. You extract the bitumen and use it. In our case, it's also desirable, but we would be extracting the sand and clay and using that. Fortunately, the ionic liquid separation process works well on drill cuttings. The ionic liquids can be separated from the powder particles via a water wash, which is great environmentally sensitive. The ionic liquids are recyclable and containable, also environmentally desirable. And so we were able to manufacture aggregates from the drill cuttings that were produced from the ionic liquid separation process. These are showing some of the aggregates before and after sintering. This is preliminary work demonstrated that we're able to make aggregates that are moderately high strength, should be useful for aggregates for construction as well as for propping gas wells with more development. More development means that we need to enhance the sintering kinetics. So back to our doped sintering studies from earlier in this presentation. And that's where the approach is. Because these are such high silica content compositions, we need to flux that silica to promote liquid phase sintering. But we can also flame spheritize these materials, as shown here. These are proppants made from drill cuttings after ionic liquid separation, aggregation, and passing through our flame tower. We're able to make quite uniform, highly vitreous beads, which subsequently, once devitrified, will perform like we demonstrated with the metabasalts and andesites. So the proppant processing technologies that we've developed work with drill cuttings, On the left, you see vitrified beads made by flame spheritization. On the right, you see commercial proppants manufactured via sintering. There are other approaches to densifying these materials. Cold sintering and cementitiously bonded systems both work. We've demonstrated that in other work that we can achieve moderate strength particles from some of these raw materials without requiring sintering cycles. Hence, no use of hydrocarbons, no production of CO2. Similarly, we're looking at other byproducts of industrial processes for proppant applications. One is the swarf that's left over from the manufacturing of ferrous-based ball bearings. All right, the swarf, or grinding powders, if you will, can be transformed back to ceramic using a flame atomization approach, which forms first wustite, which is highly fluid, and spheritizes in the flame due to surface tension, and then later in the flame plume, by adjusting oxygen partial pressure, can be converted to magnetite. Magnetite is desirable because it's magnetostrictive, which means that in the presence of a magnetic field, it changes shape. And if you put that material in an alternating magnetic field, it'll change shape in an alternating fashion, hence vibrate. If it vibrates, you can detect the material acoustically. You can also emplace the material magnetophoretically, and you can stimulate it using a magnetic and/or electric field. So this brings us into the world of a whole new proppant application that we term smart proppants, and where we're applying a fair amount of our attention right now. Smart proppants would allow us to not only place the materials using magnetophoretic stimulation, but also detect them later on, once they're in place, to understand the magnitude or the size of a propped, hydraulically fractured shale deposit. That's important for many, many reasons, ranging from understanding how the production of the well will change over time, to also understanding just exactly where is your well with regard to private property boundaries and the like. These materials may also have an application for in situ treatment of hydrofracturing fluids. By substitution of other transition metal ions instead of iron, we believe that we can make these things moderately catalytic for removal of total dissolved solids, as well as potentially T-norms, and possibly also perform well as permeable reactive barriers for remediation of contaminated groundwater. They're also useful as heavy media for heavy media separation in coal grinding and minerals processing. Those are desirable characteristics that we could develop further. And what goes around comes around. These materials now are inexpensive, spherical, refractory, colored. We can color them anything you want, pretty much. We can make them highly absorptive in the solar spectrum. So here we are back to solid thermal transfer media. So to summarize, it's been an interesting path. We've been able to demonstrate that underutilized byproducts of industrial processes are legitimate raw materials for manufacturing proppants for use in the oil and gas industry. We can manufacture them in large tonnage quantities. We extended the processing methodology to other raw materials like drill cuttings and the like, and developed quite a bit of patentable IP that subsequently has spun out to industry. Other applications and opportunities are abundant. It's only a measure of how creative do you wish to be. So some takeaways. Again, what goes around comes around. The ceramic science and the technologies that were developed decades ago were employed in these studies here to understand how to manipulate the properties of a material by manipulating the processing characteristics. We developed a suite of proppant materials that are instrumental in enhancing the ability to retrieve gas and oil from unconventional deposits, the natural gas shale boom, if you will, which created energy independence for the United States 15 years ago. However, things change. The use of fossil fuels, like natural gas, contributes to climate change. Lots and lots of evidence that burning fossil fuels, creating CO2, changes the temperature of the earth in a localized sort of way, affecting climate change, and that this is an issue that is going to be pushing us towards becoming a society with a better, lesser carbon footprint. But carbonaceous materials derived from hydrocarbons are still going to be required in our society. And that's because they're reagents, they're chemical precursors, and they're fuels for the manufacturing of glass, of steel, of polymers, of chemicals, pharmaceuticals, fertilizers, food. All of these things sustain our life. And that the renewable and alternative energy technologies that are evolving, which will supplant some of the hydrocarbon usage in the future, are going to require the use of hydrocarbons to enable them. We have to manufacture these materials to build the solar turbines, the hydro turbines, the solar cells, and so on. So we need to develop new processing science. New processing science which will enable us to do things like sinter at lower temperatures and not need fuels, not need to burn fuels for process heat and so on, in order to manufacture ceramic and other materials of sufficient quality to enable continuation of our current lifestyle and advances in the future. This is a whole area that probably is right now underexploited and a great opportunity. Green manufacturing on steroids. And beware, there are new energy technologies on the way. It's going to change the landscape. You can't pick up a newspaper and not see an article on the current fusioneers, the people who are working on fusion. And it's a broad brush of society, quite frankly. And fusion is on our near horizon. Fusion will enable us to generate electricity with a very, very small environmental impact, if any. The issue is it's going to require advanced materials. So here we are right back to the use of carbonaceous materials to enable the process heating to manufacture the industrial materials and high performance materials we'll need for our new energy technologies. So to conclude, what I learned from my professors, what I learned from my mentors, my colleagues, my friends, my students, has allowed me to apply science to developing new engineering technologies and new materials for applications that I could never have imagined when I was going to school years ago. And all of these people that I've met and interacted with and the knowledge that I've gained was enabled by the American Ceramic Society. ACerS was instrumental in enabling me to have a productive, rewarding career. And for that, I thank the society and I thank all of you. Thank you very much, and I'm happy to answer any questions.